check. 1, 2, 3. Okay. So today we are going to discuss about the method that we have given here. Is about the Newton-Raphson method. This method is primarily used to solve the equations of fx equals to 0. And if it is for equation that it's not 0, it's usually easy for us to rearrange them so that it becomes something that is close to 0. In this case, we're trying to find x by using several approximation. Okay. Please understand that the Newton-Raphson method has quite a few requirements for this to be usable. Okay. Now, one of the most important requirement is this must be differentiable in all of the domain that that is going to be used. Okay. So in the domain that we are going to use the method here, then the function here must be differentiable. Okay. But if we can find them, then the method is generally going to be quite useful because they're going to give us a fast answer for a short amount of calculation. Okay. Now, the basis of this method is that we are going to start with guess value. Okay, this guess value here for three differentiable method, they need to be close enough to the root here so that they're going to be convergent. Here's the idea. Suppose that you have a function here that's fx. I'm sorry, my bad. They must it has to find the x-axis here. We want to find this, the root when fx is going to be 0. Okay. Let's call this point A. Okay. We're going to find this the position of A here by starting from any point that is close to A. Let's start, let's say, at this point. Let's call this point as alpha. Okay. Now, the idea is we're going to find a tangent at a tangent at alpha, okay, and find the point that they are going to cut the x-axis. So in alpha, we're going to find tangent line. This tangent line is going to cut the axis, let's say, at the point beta. As we're going to see them here, the distance from alpha to A is going to be larger the distance from beta to A, which means that we're getting closer to it. So here, from the point beta, we're going to start anew and find this is going to be the new beta here. As we can see them here, f of alpha is going to be larger than f of beta, which means that the beta is a better approximation than alpha. Okay. We're going to do the same here, and from beta, we're going to make the second derivative here. No, sorry. The second tangent line. Okay. And this is going to be the gamma. As you can see them here, the f of the gamma is even better. As we go over and over again, then the value is going to get close to A, the true value, okay, fast. Okay, now that is the graphical point of doing this. Now let's see how we are going to do this mathematically. Okay, let's start with the first step, finding beta. I'm going to erase everything here that goes from here. Oops. Okay. So let's say that we have this is going to point beta. We can see here that, wait, yeah. In this case, how do we're going to find the gradient of fx at the point beta here as f dash x, okay, x number n here, okay. That's going to be f of the x here, okay, minus 0 over the value of x there, okay, minus the next method. In this case, x number n is the first step, and the next one is the beta. So we start at alpha and then goes to beta. Or if you have them here, f dash of alpha is going to be f of alpha minus 0 over the alpha minus beta. If we rearrange these equations, we're going to have that here, we're going to have the beta is going to be the alpha minus f of alpha over the f dash of alpha. This is the rule here. So the next step is going to find from the previous step here minus the value of the f over the f dash of them here. So in this case here, we just need to find the alpha. And this is the reason why we need the fx, the value to be differentiated, to be differentiable in the region that we are going to analyze. So in the region that we want to find the derivative here, the f itself must be differentiable because it's going to be on the denominator. This value can converge quite quickly, but there are, of course, there will be some point that this approximation is going to fail, okay? Which one of the most obvious one here is the cases when the derivative, as we try to find them here, ever getting into the zero. So in this case here, if by the sum derivative we ever got into this point, somehow we will not be able to find the point A when our calculation starts from a value that is too far away, that it goes into the point of zero derivative. Okay. So the f dash of alpha, if you ever get into that point here, if you ever get to point B, they will not be differentiable. Okay. Now, this is the Newton-Raphson. As you can see, the Newton-Raphson is going to lend itself to numerical method by programming very easily. Because as you can see them here, all the calculation can be done fast. The problem, of course, is that we need to find out the derivative, and the derivative need to be easily calculable. How to find the derivative if we don't have the value of them here? That will be another question. If f dash x is not analytically differentiable, yes, sometimes we can do approximation using the numerical derivative. Okay, but in general, numerical derivative is not going to be as accurate as the analytical derivative. Hence, the convergence will not be as fast as the initial derivative. Okay, so this is it. This is the Newton-Raphson method. Okay, should you have any more questions, feel free to contact me. Thank you.